Zoran Šunić, and he will tell us about conjugates of the shift map and self-similar groups.
Okay, thank you, Andre. Before I continue, let me just mention something that some of you don't know. That I'm actually a member of the Ukrainian Algebra School. Let me share my screen and I'll convince you, hopefully. Yeah.
Tu devrais écouter un ou deux exposés
See my
encore.
screen?
C'était trop fatigué, tu te bouges sur moi. Je te sens un bisou quand j'arrive.
Oops, no, that's not what I want to share. Maybe this one. No. Ah. Let me see. This is the screen.
It was an advertisement, something like that.
Oops. Let me try. I don't understand why I can't share. Okay, I think I can share now.
Just switch your pages.
Yeah. You can see my screen?
Yes, we see
Excellent.
genealogy project.
All right, so this is my advisor.
Yeah.
And here's the advisor of my advisor, which is Mark Kleiner. And Mark Kleiner studied in Kiev with Reuter. So there you go. Anyway, let's go to the talk. I'll be talking about why I can't do this. Oops. Anyway, so let's...
No, you have to erase cycles. They are on the screen.
That's fine.
And blue, also blue.
That's fine. The blue is fine. I was just testing it. Okay, conjugates of the shift map and self-similar groups. It's all joint work with Slava. So let's talk about it. Let's start with this Collatz map. Everybody knows about the Collatz map. It's defined on integers simply by if your integer is even, if your positive natural number is even, you divide by 2. If it is odd, then you calculate like this: 3n plus 1 divided by 2. That will be another positive integer. So it has been checked for all positive integers less than 2 to the 71 that if you iterate this map, eventually you'll be trapped in this cycle of length 2. 1, 2, 1, 2, 1, 2. And it's a conjecture that this is true for all positive integers. Of course, we don't know how to prove it. It seems to be very, very difficult. Now, this map defined on positive integers can be extended on this dyadic integers, if you want, to the ring of dyadic integers, using the same formula. T of 2z is z, just divide by 2. And this is another way to write the previous map. So T of an odd number is T of 1 plus 2z is mu2 of z, where mu2 is this simple transformation, 3z plus 2. Okay, and that extends the original map to the ring of dyadic integers. And of course, dyadic integers can be nicely represented by infinite binary sequences. So write infinite words, if you will. So this dyadic integer can be represented by this write infinite binary word. And when we use this symbolic way of representing dyadic integers, this Collatz transformation can be written in this way. So T of 0w is w, that's literally dividing by 2. and T of 1W is 1 is ignored, and the transformation 3z plus 2 is applied to the tail W. So that's the symbolic look at the transformation. And why can't I move? Okay. All right. So in 1976, Terras, while studying this interesting problem, the Collatz conjecture, came up with a certain map from dyadic integers to dyadic integers. Namely, you apply gamma to any right infinite word, and you create a sequence y0, y1, y2, y3, and this sequence is just the parity of the numbers as you see them. So as you start with your W, so it has certain parity, it's even or odd, that's your y0. Then you calculate T of W, it is even or odd, you just record the parity. Then T squared of W, it will be even or odd, you record the parity, and so on. So that's the map that Terras defined. And interestingly enough, this map is actually, first of all, it's a prefix preserving bijection from dyadic integers to dyadic integers. You obviously see that eventually this will be triautomorphism. So gamma is actually triautomorphism, but we'll talk about it later. The interesting thing is that the Collatz conjecture can be expressed in terms of this map gamma, simply as saying that gamma of positive integers lands inside 1/3 of z. So, okay, and then the best result I know about Collatz conjecture is still this result of Terras from 1976 that says for almost all positive integers, the keyword is for almost all positive integers, the orbit of n reaches a number smaller than n. If we could prove that for all positive integers you reach numbers smaller than n, that will prove the conjecture. But unfortunately, it's only true with this word almost. And there's some small improvement by Terence Tao in 2019, but it's very much similar in spirit, at least, to the result of Terrace. So that's still the best result we have. Now, this map, gamma, it has been observed by Lagarius that it actually conjugates the usual shift map. You see, if you recall the definition of the Collatz map in this symbolic way, T of 0W is W. That's literally what the shift does, the one-way shift on binary strings. And T of 1W was, well, you apply mu2 to W. The shift doesn't do anything, but in some sense, you see a similar structure of these two maps. And actually what happens is that gamma, the map defined by Terras, he didn't use any trees or conjugation or anything. He was just looking at parity. But nevertheless, what happens is that gamma conjugates between the usual shift map and the Collatz map. Okay, so we have that relation. Now, there's a Lagarius in his work also proposed a conjecture called periodicity conjecture. If you look at Z2, the rational dyadic integers, those are the rational numbers with odd denominators. And symbolically, you can recognize them as those right infinite sequences that are eventually periodic. Okay, so the conjecture says simply that gamma of rational dyadic integer is the set of rational integers is also a rational dyadic integer. And if you prove this conjecture, you will prove, in a sense, a weak version of Collatz conjecture, because at least you will prove that all trajectories of t on integers are finite, eventually periodic. So you will not prove that everybody reaches 1, but at least you will prove that there is no divergent orbits, that every orbit has to end up in some cycle, some finite cycle. So that's a weaker version of the original conjecture. Okay. Now, Bernstein in 1976, actually, I think this is wrong. date. Sorry about that. It's later. 1976 is the date for Terra's work. So this is later. I forgot exactly the year. Certainly 90s, I would say. Provided a formula for the inverse of gamma. So gamma was the map defined by Terra's, but Bernstein provides a formula. Don't worry about the formula, it's not important. There's an explicit formula that he found for gamma inverse. And he proved that when you apply gamma inverse to rational number, you get a rational number. So in some sense, that's 1/2 of the periodicity conjecture. Unfortunately, the other half, namely this half, is the one that implies that all trajectories are finite. So the proof that Bernstein has is all nice and everything, but it's not the half that we need. It's the other half that we need to prove that all orbits are finite. Okay, so I already mentioned we will, of course, we'll look at gamma as a three automorphisms because it acts on right infinite words, binary strings, and it preserves prefixes. So clearly we are talking about three automorphisms. So very quickly, of course, given some alphabet, in this case 0, 1, we can form the rooted tree, in this case binary rooted tree in the usual way. And we look at the three automorphisms. Again, I will not distinguish too much between three automorphisms of the actual tree X star and the action on the boundary of the tree, which is the right infinite words. If you know how to act on finite words, you know how to act on right infinite words as well, and vice versa. So there's really no big difference. So I may sometimes say acting on finite words, sometimes on raised, but it doesn't really matter. The notion of a section is important, of course, so let me mention it yet again. It was mentioned before. If I have some arbitrary automorphism and some vertex U, what is a section? The section is the action of G inside the subtree with root at U. And you actually ignore what happened. So G acts on UW somehow. It goes here and then who knows where. So what you're recording is whatever happened to this W. W goes here to some W prime, and that's what you're recording. So W goes to W prime. That's what the section does. Okay, so GU of this W is W prime. Okay, so just to emphasize it again, the sections themselves are not restrictions to this subtree. They are actually elements of the full group of three automorphisms. Okay. All right. So, and then group is self-similar if all sections of all of its elements are also elements of the group. That's the definition of a self-similar group. What is a finite state automorphism? Finite state automorphism is an automorphism that has only finitely many different sections. So there's infinitely many vertices, but the actual automorphisms defined by all those sections at those vertices, there's only finitely many distinct ones. So that's a finite state automorphism. And you can have many, many examples, but for this talk, this is the important and relevant example. You can create a nice finite state machine that multiplies by 3 dyadic integers. It's an easy exercise, like the map 3z plus 1, for example. How do you define 3z plus 1? When you read 0, 3 times 0 is 0 plus 1, so you write 1, and then there is no carryover. So after that, you're just multiplying by 3. How do you do 3z plus 1 when this digit is 1? 3 times 1 is 3, plus 1 is 4, so you write 0, and we are in binary case, so I have to carry over 2. So for the rest of the word, I have to apply the map 3z plus 2, and so on. So there's only 3 states, 3 distinct states if you do this carefully. And you have nice finite automaton with 3 states that will teach your dog even how to multiply by 3 or calculate 3z plus 1 or 3z plus 2. Okay, so there's the finite automaton that I was referring to with 3 states. Now, here's a more general setup that we kind of developed with Slava. Instead of just using identity and mu2, as is the case for collets, so for collets, these two maps, alpha 0 and alpha 1, are identity and mu2, 3z plus 2. But you can use any three automorphisms. So define a map T by using T0W is some automorphism applied to W, and T of 1W, another automorphism applied to W. Then you can prove that the unique automorphism gamma that preserves parity, which means literally fixes the first level or fixes the first digit, and satisfies and conjugates the shift map to T, is given like this. So gamma has as a left section gamma alpha 0 and as a right section gamma alpha 1, where alpha 0 and alpha 1 are these maps. By the way, as I said here, this is not valid only for the binary case, but I don't want to discuss the generalities. It's very, very similar, so you can guess. And what we proved actually is that if alpha 0 and alpha 1 are finite state automorphisms, then this inverse map, the inverse of gamma, actually preserves rationality. So this is literally the Bernstein result, except generalized to all possible automorphisms of the three, finite state automorphisms of the three. Okay, sure. And now the contracting case is also interesting. So if alpha 0 and alpha 1 are finite state automorphisms, and moreover the group generated by alpha 0 and alpha 1 and all of their sections, it's a finitely generated group. If that group is contracting, then this map gamma is actually finite state. And because it's finite state, then this will be true. The periodicity conjecture will be true. That's very easy to see. Unfortunately, this is not good enough for the Collatz map, because the group generated by the sections of alpha 0 and alpha 1, in our case, alpha 1 is this guy, and the sections of that guy are mu1 and mu0. So the group we are looking at is this group, which is Bounce-like-Solitaire group 1, 3. We know that from old work with Zoran. Anyway, it's a very simple group, but it's not contracting. And because it's not contracting, this does not apply, so we cannot prove periodicity conjecture just so easily. So it's tough. But in any case, whenever we have contracting case, then periodicity conjecture, rational numbers will go to rational numbers. I will not define contracting group. I think most people in the audience already know. Basically, contracting group means that as you go down and you look at sections, the sections get shorter. So that's what contraction really means. So once you go deep enough, all the sections become smaller in length. All right, now going back to the interesting conjectures. So now we are discussing a triautomorphism, a single triautomorphism. And Collatz conjecture literally can be rewritten in this sense by saying, if I want to prove Collatz conjecture, all I have to prove is that gamma applied to any word that ends with 0 tail actually ends eventually in 1, 0, 1, 0, 1, 0. That's all you have to prove. So gamma applied to words that end in 0 infinity go to words that end in 1, 0 infinity. That's all. That's Collatz conjecture. Periodicity conjecture in terms of gamma, of course, it's already clear. All you have to prove is that for this triautomorphism gamma, when you take any eventually periodic right infinite word and apply gamma to it, you will get eventually periodic word. So it sends eventually periodic race to eventually periodic race. Now, to give you a couple of simple remarks on this situation, so obviously we have a semigroup here. If you look at all automorphisms of the rooted tree that map eventually periodic race to eventually periodic race, it forms a semigroup. Composition will also preserve eventually periodic race, so you have a semigroup. Interestingly enough, this is not a group. So it is possible to have a triautomorphism that sends eventually periodic words to eventually periodic, but the inverse does not. Such examples were not trivial to find, at least not for me, but we found such examples with Slava, so we know that this is not a group. Of course, you can define a group, obviously, now by saying, all right, take all the triautomorphisms such that both the automorphism and its inverse preserve eventually periodic words. That will be a group. And that group, it's not difficult to show. It's a self-similar regular branch group branching over itself. So it's a huge group. It's dense in the full group of automorphisms. It has cardinality of continuum. And it contains a copy, actually, of this group, and so on. It actually contains a copy of a group that ŠunićConjugates and Volodya Nekrasevich were studying in year 2000. It contains the group of so-called Wycliffe binary automorphisms. So it's a large group. Okay, so in this remaining time, I just want to say only a few things that we proved for this specific case of collage. So the previous results were more general, discussing the general situation. Going back to the specific situation for the collage map, we can look at the sections of gamma and we can calculate. The section on the left of gamma is gamma, the section on the right is gamma mu2. Remember the definition of gamma was gamma is gamma and then gamma mu2, where mu2 is the map 3, x goes to 3x plus 2. Anyway, so here's a couple of levels. The circled, the states that are circled are the active ones, where there's a flip. So there's a flip, and actually it's very easy to recognize where you have a flip. The number of appearances of mu1 has to be odd. Then the state is active, otherwise it's not active. All the states of gamma have the form like this, gamma and then some product of this mu0, mu1, and mu2. Remember, those mu0, mu1, and mu2 come from bonds like Solitaire group. It's a just multiplications. And in particular, all such automorphisms of the 3 are states of gamma, as long as this I0 is not 0. So as long as I0 is not 0, every such expression will give you a state in gamma. It will give you a section of gamma. Okay? Yeah, and I already said the active sections are the sections with odd numbers of appearances of mu1. Well, we have kind of better understanding maybe of gamma if we look at the minimal automaton. So we were able to basically understand the minimal automaton of gamma. Here I have some kind of diagram trying to explain how it looks. So there's the gamma right there. There's gamma, and then the left section of gamma is gamma, the right section is the gamma 2. Now I have certain encoding. Don't worry about the numbers. All I care at this moment is just the structure of the minimal automaton. So you have this infinite ray, and then there's short cycle of length 2 hanging, and then another cycle of length 6, and then cycle of length 18. And these cycles are getting larger and larger. That's the size of these cycles that are hanging. And going down from a state to a state in these cycles is dividing by 2. So again, I have certain encoding. The encoding is more or less clear. The encoding is, instead of recording something like mu1, mu1, I would call this 4. This is just 1 ternary is 4. So code for this state will be 4. Code for this state will be 8. That's 2 is 8 in ternary. Anyway, so that's the encoding, but going down is literally dividing by 2 modulo wherever I am. So if I'm here, when I'm going down, I'm dividing by 2 modulo 27. So that part of the structure is very simple. The complicated part is going to the right. Going to the right, wherever I am, say I'm here. When I'm going to the right, I have to take this number, multiply by 3, add 1, and divide by 2. If these two things looks familiar, well, they should. But the calculation is modulo, again, when I go from here to here, I will multiply by 3, add 1, divide by 2, but that whole calculation will be done mod 27, and then I'll get to 20. Anyway, my point is we have clear understanding how the minimal automaton of gamma looks like. It's infinite. It has exponential growth. That's not obvious from the picture. The point is that these red things are kind of mixing things sufficiently so that you can reach exponentially many things as you go to the right. There is things to prove, but what we can prove is that you can reach any vertex, say, in this third cycle in no more than 9 steps. In general, you can reach all the vertices in the k cycle in no more than 3k steps, and there's exponentially many vertices from here to here, so that proves that you have exponential growth of the minimal automaton. But on the other hand, another thing is interesting, that if you fix a state, so that's this proposition that minimal automaton is exponential growth. But if you fix a state, some state, say this one, and you ask yourself, what is the language of words where this state appears as a section? That language is actually regular. And not only is regular, but it's of polynomial growth. So in some sense, when you fix a state, situation is easy. And the reason is, again, if I want to say understand the language of words that have 13 as a state, well, there's only, you see, once I move there, I can never see this state again. So it's actually fairly easy. I can ignore the rest of it, and I obviously have a finite automaton that tells me how to recognize all the words that end up here. And that automaton will have polynomial growth because these cycles are kind of, again, I cannot go back from this cycle to this cycle. I can only go from one cycle to the next, to the next, to the next, and that's it. There's never going back. So the growth is polynomial for these languages. Okay, and that's pretty much the only result I wanted to share at the moment. I'm running out of time. Just as an interesting challenge for the experts, here's the histogram of eigenvalues of the following group. You take the Bamslag-Sauter group generated by mu0, mu1, and mu2, add gamma to it, and here's the empirical density of eigenvalues. What you can see is that the second eigenvalue does not grow very fast. I suspect we have expanders here, but that will be interesting to prove. Okay, we have a huge gap. Okay, so let me stop right here. Thank you.